Okay, so we're going to talk about the world of Webb, the cosmic circle of life, and viewing the universe through the eyes of Einstein. It's a great pleasure to be back. I used to work here until we got moved to a different school. Um, a very large cast of collaborators, a number of which are in the room today or in Zoom, plus 110 more worldwide over 18 time zones. Um, this is a Webb image, a mosaic of the North Ecliptic Pole Field made by Rolf Jensen and some of my undergrad grad students. Um, Whenever I talk about a distance, the average galaxy here is 10 billion light years away. The lateral size, the field of view of the image, is roughly that distance divided by 1,000. So you're looking at about 10 million light years across here at that distance. Yeah, keep that rule of thumb in mind. This is the only formula I will use today. I can help it. So here's the agenda. Webb in orbit as of Christmas Day 21. Wonderful Christmas gift. Then the first images of Webb and the cosmic circle of life. And then the main part of the talk, viewing the universe through the eyes of Einstein. I'll have some conclusions and I'll have a couple of spare charts and some complementary things, but we won't get to that. There's a link here. There's also a V2 of this talk. They're barely different that Matt or Juliet can post around. So first, a general warning. Asking NASA for Hubble data is like taking a sip from a fire hydrant. Hi, Fernando, good to see you. Children, please do this. Don't do this at home. Taking NASA's Webb images is like taking a sip from the Niagara Falls. So please don't do this too. If you're overwhelmed with images, don't blame me, blame NASA, please. Okay, so Webb was finally launched on Christmas Day almost 4 years ago from French Guiana. It did have a strong European and Canadian participant component, although the project was led by NASA. So here is Webb above the Gulf of Aden and Saudi Arabia and Africa shortly after its launch. It left the Earth immediately. It didn't orbit. It just went straight to the L2 Lagrange point, which is about 4 times the distance of the moon. So here's the first image. 2 months later, February 22, it took a selfie to calibrate itself. All the mirrors are there. This one is overexposed because of the lighting. So you look at a star and you get 18 out of focus images. The thing has to be cooled down to 45 Kelvin, and of course it left at room temperature. So it took a while to cool down and to focus all the mirrors. But when all 18 mirrors were focused, you saw this. They were, of course, not properly co-aligned yet, but at least they were focused. And then with 7 degrees of freedom, a push and a push, a push and a pull, a tip and a tilt, a rotation and a translation, and a radius of curvature, you could put them all on top of each other. And now you have a single image of a star, the way it's supposed to work. This was in March of 22. The 6 diffraction spikes, of course, in this horizontal thing are the Fourier transform of the hexagonal mirror structure. There's 6.5 meters worth of mirrors. Each is 1.35 meters across. And the space between the mirrors gives you this lack of information. And that's the Fourier transform of the vertical support bar that holds the secondary mirror. My friends at Goddard Space Flight Center who made this image were very excited about it. They had focus, but they also saw background galaxies. They thought that was even more interesting because that's what Webb was designed for, after all. So we're looking back in time. There is 5 cameras, spectrographs on board. The European HOOPS, near-infrared spectrograph and mid-infrared imager, they all look at different parts of the sky. The U of A near-infrared camera, and then the Canadian fine guiding sensor that holds the telescope still while you take long exposures, retrieving the image of unsaturated stars and telling the gyroscopes and the reaction wheels to move, plus a near-infrared slitless spectrograph that we got folks working on here, including Vince Estrada, and the whole shebang works between, well, almost 1 microns, 0.9 is the shortest usable wavelength, all the way up to 28 microns. You see 1 to 8 microns here. So everything was working. This is an image of the Large Magellanic Cloud. So you can see there was progress compared to the old 85 centimeter Spitzer Space Telescope at the same wavelength with 6.5 meters. We get 8 times better resolution. Not only can you see the plenty stars in the Large Magellanic Cloud 160,000 light years away, but also the gas and the dust between the stars. So, yeah, before we get to the cosmic circle of life, I really have to get to the periodic system here. The periodic table that you learned about in high school is incorrect. So let me summarize. In blue, there's hydrogen and helium, the only chemical elements made in the Big Bang. In green, there is the elements made primarily in low mass stars like the sun that eject their outer layers when most of the hydrogen helium is used up, burned up the end stages of their lifetime. In yellow, you have the supernova explosions, either massive or with the help of white dwarf stars, type 1As. And in purple, you see the elements mostly made in neutron star mergers, as we have known primarily recently from the LIGO work. Why is this periodic system incorrect? Simply because this is the correct one. Yeah, 76% hydrogen, 24% helium in the Big Bang. And then the rest, which astrophysicists refer to as metals, and astronomers like me refer to as dust, was made inside stars. So hydrogen and helium and metals or dust, as the case may be. So planets and people are literally made from the leftovers of these low mass and massive stars that produce these elements at the end, well, during their lifetimes, and ejected it at the end of their lives. And that is then the basis of the cosmic circle of life. So to put this all in perspective, in blue, you have the cosmic star formation history. That's the blue parabolic looking curve. This is the redshift axis. This is the cosmic time axis. We're here today. The Big Bang would be over there. And the age is roughly 13.8 divided by 1 plus z plus some higher order terms. And star formation started early, as we now know, redshifts 14 to 16, not shown here, peaked around redshifts of 2 to 3 when the universe was only 3 or so billion years old, and then declined. The same is true for the resulting supernova rate in red or yellow, as well as the growth of the active galactic nuclei, the supermassive black hole growth in green. It all sort of happened together, and it peaked around redshift 2, 10 billion years ago. Therefore, for an average blue star-forming galaxy like seen over here at this median redshift of 2, Hubble is the primary telescope to see this, because here's where Hubble is essential. While you go to higher redshifts, the infrared filters and even beyond 5 microns, the mid-infrared imager spectrograph from Webb are essential. And there is an area of overlap where you can use both. So Hubble best samples the unobscured star formation, and Webb best samples the obscured parts, plus the very high redshift galaxies. Oops, yeah, good. So this is a slightly more complicated graph, but it's important to understand. If you were a fly with a fly's eye, you had no resolution, spatial resolution, you just had wavelength coverage. This is what you would see in the sky between 0.1 microns and 1,000 microns, which is 1 millimeter. This would be the reflected light in physical units coming from the solar system. It's the spectrum of the sun, almost 5,800 degrees as reflected off the dust in the solar system. The average stars in the universe produce these red dots, and it looks like the spectrum of the sun, except it is way further down in amplitude, and all redshifted, of course, because the average redshift is 2, as I just said. Now, then there's another hump over here that peaks at a few hundred microns, which is actually stronger than the collected starlight, and that comes from the dust. So 1% of the elements in the universe, everything else but hydrogen, helium, produce just about as much energy in the far infrared as stars produce in the terrestrial ultraviolet optical. Keep that in mind. So dust actually wins here. And then, of course, the cosmic microwave background is not shown here, peaks around 1 millimeter and goes through the roof in amplitude. So we're going to keep this in mind. There is stars and there is dust. Okay, So the image to the left, many of you have seen when it was first shown here on the second floor in 1995 by Professor Jeff Hester and Paul Scowen, made it onto a US postage stamp. It's the Eagle Nebula, a cosmic cradle of star formation, pillars of dust a few light years long that are being shone upon by bright stars, not shown here, but later on north of the field of view. And it is the ultraviolet radiation of these bright stars that sculpts these pillars and that allows new stars, low mass stars, like the sun to form. Here you see the same in the near infrared with Webb, much higher resolution, of course, and at the longer wavelengths, you also get to peer through the dust more carefully. The pillars are still there, but you can now see the stars like the sun forming at the end of these pillars. So this is a cradle of cosmic star formation. Here you see the same in the mid-infrared, 8 to 15 microns with MIRI. It's tilted, but again, you can see that at the end of all these pillars that are being sculpted by all these bright stars off the field here and triggering formation of new stars. This is a common process that is true everywhere in the universe, also in nearby and even in distant galaxies. Here's the Large Magellanic Cloud again, 160,000 light years away. A bright blue star cluster here, massive stars that live fast and they die young, and they sculpt the gas, surrounding it in this cavity over here. If you look at an enlargement, in this case in the UV optical from Hubble, you can see that this massive star cluster sculpts this dust, and at the end of this finger, it sort of looks like the finger of my hand, is a star that you can't see in the optical, but you can see it infrared. There it is, a star like the sun forming, courtesy of all these short-lived massive stars that produce the ultraviolet radiation. This was one of the first images that came out with Webb over 3 years ago, the cosmic cliffs of star formation in the Carina Nebula, 7,600 light years. And again, it's the bright stars on top, the short-lived ones, that produce the ultraviolet radiation that sculpt what I call this cosmic beachfront. No water, just ultraviolet light, no sand, just dust. And inside this dust, especially in the mid-infrared, you can see stars like the sun forming in great numbers. In fact, many stars that form don't form singularly, but they form in small star clusters or in binaries. The sun is lucky that it's alone. Here's another example in the Orion trapezium that you can see with a small telescope. And the enlargement of this beachfront over here shows a young star in formation that contains the carbon chain methylcation. I wouldn't know the chemical formula for it, but chemists in the audience would probably know that. Long carbon chains are actually quite common to see in these protoplanetary nebula. This is the Hourglass Nebula. A young star is being formed right here with a protoplanetary disk, only 100,000 years old. And if you wait long enough, all this material will be blown away and the star will start shining and the planetary disk will start forming its own planets, all courtesy of the gas and dust that was produced by previous generations of stars. Here's another high-resolution example of that, the Rho Ophiuchi dark cloud, both in the near and mid-infrared stellar nursery, only 450 light years away. A couple of new stars already formed. There's another star forming here, spinning fast and throwing out these jets that contain a lot of polycyclic aromatic hydrocarbons, PAHs. That's a fairly common way for stars to form. It's messy. It's not very efficient. Not all the material gets used up, but that's okay. That will come in another generation. Here's another example of that. The new star is now already visible, Herbig-Haro 4647, with the jet expelled material at 1500 light years. So that's how the cosmic circle of life works. In this process, of course, also protoplanetary systems form, in this case around the star. You can see with the unaided eye, Fomalhaut in the southern winter sky. The star itself is suppressed here with a cold finger in the camera that we call it a coronagraph that suppresses the starlight. But you can see the protoplanetary rings quite well. This is where Saturn would form if this were our own solar system. Actually, a little clump is already forming there. You can call that a proto-Saturn or a proto-Jupiter. very common. Here's another example of AU-MIC, 32 light years away, about 60 astronomical units across. So Jupiter would form right here, and the star again is suppressed at the central location with the cold finger. Here is an example of a planet seen next to the star. The star with this phone number again is suppressed with this coronagraph. The planet is primarily visible in the mid-infrared. It has some side lobes in the near-infrared, but it's there all right. And it's pretty massive, 10 times Jupiter. And it's also pretty cool, although it is only 15 mega years of age at this point. Here's a spectrum in the near-infrared of one of these Earth-like exoplanets. Well, actually, it's half Jupiter in mass, so it's not really Earth-like. And while there's many water features visible in this infrared spectrum, the temperature of this planet is 1,000 Fahrenheit. So that's actually not water, that's steam. Yeah, but there you go. We can find planets with water. Good. So let's see how we're doing time-wise. Matt, you keep me accountable, right? So how does this matter get out? Well, the Southern Ring Nebula, we will see the northern one in just a minute, is the end stage of a not so massive star like the Sun. And after a few billion years, 5 billion years for our Sun, it will start throwing out its outer layers. It will have burned hydrogen and helium in the core, and then in the shell, and then it starts helium burning also in the shell. And at that point, the star gets so hot in the outskirts that the outer layers get driven out together with all the heavier elements in the periodic system that have already been made. So these outer layers are then expelled, and the star itself increases in size to about 100 times its original radius. The Earth is at 100 solar radii, so we would be swallowed up by this process. Yeah, this is called a planetary nebula. It's not a planet, but it looks like a planet if you don't look carefully enough. The astronomers that were studying this were very excited about this little elongated thing in the background. It turns out to be a galaxy. Here it is in the mid-infrared, an edge-on galaxy with a center, and if you look hard enough, you can find galaxies everywhere. On average, there's about 100 or 1,000 times as many galaxies in any of these images than stars. So let me summarize this. This is the Northern Ring Nebula in the constellation of Lyrae. Again, the outer layer is being driven out in what we call the asymptotic giant branch stage, where the helium stops burning and the star starts losing its outer layers. And this is how our Sun will come to an end in 5 billion years, and leave a hot, very dim white dwarf in the center, which I'm not sure you can see here, but one of the folks in the Zoom audience, our dear colleague Sander Starfield, studies these kinds of objects. I put this text from Genesis down here because it's so applicable for dust thou art, and to dust shalt thou return. This is true for people, as we know. It is true for stars, and it is true for planets. You can see the process in action here. Here is not the same, but the analog for very massive stars. The previous one would be, 1 solar mass or half a solar mass that do this kind of stuff. This is a 30 solar mass star called the Wolf-Rayet star, very bright in the ultraviolet, very short-lived. And before it turns supernova, it starts already expelling its outer layers, showing all this mass loss. So this is a prelude stage to the supernova explosion that will soon follow. Again, here too, for dust thou art, and to dust shalt thou return. This was a supernova that went off shortly before I arrived here in 1987, also in the Large Magellanic Cloud, and it has been studied here carefully by folks like Professor Starfield. You can see the shells that were expelled before the supernova explosion being lit up almost like an hourglass set of bubbles. And here's an mid-infrared image of the Cassiopeia supernova that went off a few hundred years ago. And what is left, other than a neutron star, is just all this massive amount of dust that lights up at various wavelengths. So to summarize the first part of the talk, All galaxies have this star formation process where hydrogen gas in the top near infrared image, and rendered in red, in this case in spiral arms, will turn into stars, which in this wavelength are the little white dots in all these holes that create the Eagle Nebula type effect. And when these stars die, young or old, massive or not, they will release the dust at 1% at the bottom of the periodic system that makes it everywhere into the interstellar medium and forms new stars and new planets. Yeah. So through dust thou art made, stars in the upper image, and dust shalt thou return. It's the cosmic circle of life. And it is true everywhere we look. It is not just our galaxy or our solar system. For any galaxy we have looked at, irrespective of their precise shape, this same process is happening. So star formation and dust production is ubiquitous throughout the universe, and the cosmic circle of life rules throughout the universe. And Webb has really made this very clear to us. I'm just about halfway done through the talk, and rather than steaming on with the second part on relativity and gravitational lensing, I'll pause for a few minutes here to see if there's any questions on the cosmic circle of life or the Webb telescope itself.
Day one, just check. The focusing of Hubble, is that mechanical actuators?
No, Hubble.
Oh, sorry,
Webb, yeah. So there's these hexapods. There's 6 of them. They're redundant underneath each mirror. Each mirror is a couple of these floor tiles in size, hexagonal, and they're placed in locations where they can push and pull, rotate and translate, and then radius of curvature. Well, they set it to a nominal value at launch in room temperature, and then they know from the laboratory measurements how much out of focus that is. So they preset it for what it would be like at 45 Kelvin. And then when you come there, everything is a mess. Well, it's self-calibration. You know the star needs to be point-like.
what external control do you have over that focus?
Oh, well, you have a lot of control over it. See, the mistake we made with Hubble is there was 0 control. And had the mirror been perfect, that would have been fine, but it wasn't. As you may remember, you're young enough to remember the initial mess from Hubble. And so here in the what we call the wavefront sensing and co-alignment of the images, you get initially 18 images that are badly out of focus. But you know that this one is so bad because that mirror segment is tilted, and you untilt it until it starts to look better, like these that were already okay. This one was pretty badly out of focus. So you move it. Basically, you study the Fourier transform of each of these, and that then tells you, yeah, with nanometer precision. Yeah, yeah. Well, okay. So since the telescope optics are nearly perfect, except for these diffraction spikes here, once you feed it through a coronagraph, you know that that central hole contains, more than 99% of the light. So the star goes away. Yes. Oh, this light never makes it to the detector. You put in the Fourier plane the equivalent of a cold finger there. That's and of course you put the known star right there where the cold finger is, and you suppress that starlight, and the rest of the surrounding light goes to the detector. Yeah. Sure. Other questions? Yes, over there, and then Kevin. Yeah. Yeah. Yeah, that's a good question. In the late stages, some of them do. That's so you talk about the heavier green elements. That's really a question for Professor Starfield, who teaches this stuff. But some stars manage to do that. Now, to be frank, if you pick Mercury, not all of the Mercury is made in low mass stars. A fraction comes from neutron star mergers. Yeah. 81 is tellurium, I think. Yeah, I'm guessing here. Yeah. Well, it depends on, like for the massive stars, for instance, get pretty hot in the center and produce these elements. And the merging neutron stars, of course, even more energetic and produce most of these. If you ask me how come that stars like the sun still produce some of this, or mercury and lead, that I do not actually know. There may be somebody in the audience who can answer that question. Kevin, you had a great question, though. Kevin, you had a question. Which one? This? That's hydrogen gas is rendered in red here. Oh, that's the older stars that in the infrared show up, sort of in the mid wave band, so it looks white, but they're infrared shining stars. Correct. Yeah, all of these white, you can even see it here. That's a bright star, but there's many stars and star clusters in these holes, and these star clusters excavate the hydrogen, which is the surrounding red gas. Yeah, including the stars that are unresolved. There's many pixels that contain hundreds or thousands of stars. So they just make Milky Way light. Yeah. Exactly, great question. So for the sake of time, I should move on. The eyes of Einstein. So Albert predicted many things correctly, yet he doubted them. Gravitational lensing, the bending of light, black holes, the Hubble expansion, the cosmological constant. There's maybe even more. He opens up his gravitational lensing prediction paper that one of his colleagues asked him to do in the 20s, I think. Say, one-page paper where he just gets the Einstein radius exactly right, correctly predicted. Says, I don't really want to do this calculation because I don't think it can ever be observed, but I'll do it for my friend anyway. Then, of course, black holes he really didn't like. And the Hubble expansion he predicted but didn't believe, so he introduced lambda to make it go away, and now we're stuck with both. We have Hubble expansion and we have lambda, and if you talk to Kevin Croker, lambda may not even be constant with time. So we call it dark energy these days. Anyway, let's go talk about that. Mark or Matt, we can't really turn these lights off, right? Because they shine on the dark skies. All right, here's Stephan's quintet. 5 galaxies, 1, 2, 3, 4, 5. This one is in the foreground. The rest is at 290 million light years. They are a cosmic train wreck, a merger that's about to happening or already happening, which was much more common in the past for galaxies to merge. And sun-like stars form in the aftermath of these cosmic fender benders. This is not a major merger. This is just the kind of stuff you don't pull over for on the freeway. But it will eventually result in a big merger. And so you can see here this green mid-infrared light is the molecular gas that's being pulled out during the galaxy collision. Again, this blue object is in the foreground. This object here on the north contains a strong central point source, and that's the location of a supermassive black hole. A black hole, of course, is a region in space-time where the escape velocity exceeds the speed of light, so you can't see it, but the area surrounding the black hole can become extremely bright, and lo and behold, this galaxy has a supermassive black hole in the center that's feasting on the surrounding gas. I will refer to those from here on out as the beast. I will explain in a minute why. This is an ordinary spiral, not unlike our own, 48 million light years away. Beautiful spiral structure here, primarily seen in the molecular light of the dust that is made by the stars and the star clusters that you see here around these red dots. Here's a particularly galaxy with a central monster that is bright enough that you can see the star-like structure from the point source that's in the center. That's the accretion disk from the supermassive black hole. And here's an even more exotic example. I need to turn my phone off. Sorry about that. boss is calling. And this one is particularly red. You can see that in the red diffraction spikes, and that's common because the supermassive black hole is often surrounded by a good bit of gas and dust, and that reddens the light. The accretion disk itself can reach X-ray temperatures of 10 to the 7 or more degrees. It's the ultraviolet part that we see in the UV optical with Hubble, even if it's redshifted. And it's the optical part of the accretion disk a little further out that we see redshifted into the infrared. Many of these galaxies have this central asterisk-like feature because they have supermassive black holes in the center. In this case, the black hole also manages to expel gas at very high speeds, not from the Schwarzschild radius itself, of course, but from the strongly rotating area surrounding it. This was one of our first images in our own project with Webb about three years and a few months ago. An overlapping galaxy called VV191, a background elliptical with a spiral galaxy like our own, not our own, in the foreground. Why did we observe this? Because the dust and the gas in the spiral arms, and from the center to the edge, this is about 100,000 light years across, the sun will be here somewhere. The rather regular light from the background elliptical galaxy, which is almost at the same redshift, but it's behind it. They haven't merged yet, but they'll probably do someday. That regular light allows us to see the imprint of the dust from these spiral arms. And that allowed us in this paper to say that these dust grains from the same process that we talked about all over before are a little smaller than in our own galaxy, but that's maybe because we're further out than where the sun would be. Also, one of our students, Jessica Berkheimer, found 150 globular clusters in these elliptical little point sources that you see here and there, the pepper and salt. And those are the earliest star clusters that formed very early on when this elliptical was made, maybe 12, 13 billion years ago. Both published, as you can see here. The other thing we saw in this elliptical galaxy, there was an arc-like structure and a counter image here, which is a dusty spiral galaxy just like this, that happens to be behind the elliptical, and due to the gravity of this 10 to the 10-ish solar mass halo, the image of that galaxy, not this one, but one just like it, gets stretched into an arc and a counter image at 4 o'clock. And that gravitational lensing is very common. It was particularly common in this image of SMACS 0723, the first image that was supposed to be released July 12, 2022. It was released a day early by President Biden. One of the guys in my team selected this target. His name was Dan Coe. Another guy in my team analyzed it, Anton Kokomor. And they made this image a few days before. They sent it up to the Space Telescope Science Institute director, who fell off her chair. She sent it up to Goddard Space Flight Center, where the center director fell off his chair. And then they sent it up to NASA headquarters, where the administrator fell off his chair, and he sends it up to the OMB, where they really liked it. They sent it up straight to the Oval Office, and President Biden decides to release it a day earlier. Fortunately, he was called away from the press release by his national security advisor, so he hadn't had a chance to scoop us on the Nature paper. But anyway, there it is. Many arc-like structures from this very massive cluster of galaxies. The whitish looking galaxies are a redshift 4.4, about 4.5 billion years in the past. And they do indeed lens and distort many of these orange looking background galaxies into these arclets. So it's gravitational lensing in action. These white galaxies here at 4.5 billion years distance, when the Earth was formed, are already 9 billion years old. So there's galaxies in this image that today are 3 times older than the Earth and the Sun. Stated differently, we're kind of like a cosmic afterthought in our solar system. This was the Hubble image. For comparison, that's the Webb image. Okay, now here's some more examples of gravitational lensing. This is a cluster, never mind the phone numbers. It's seen at redshift almost 10 So the cluster is not, the cluster is really only a quarter of the Hubble time away, but it triply lenses a galaxy that's seen 400 million years after the beginning, roughly redshift 10. And that galaxy is really behind the cluster. Again, this is about 10 to the 15 solar masses. I used to be able to say that there was just about as many pennies in the national debt as there are stars in a cluster of galaxies. That's not the case anymore. A cluster of galaxies has roughly the same number of stars. National debt increases, but there is, 10 to the 15 solar masses here, and that's good enough for gravitational lensing of a point source, or in this case, a double galaxy right behind, to produce 3 images there, and here. And you can see they look the same, except the orientation is different, because the light paths from that distant galaxy behind the cluster to our eye across these 3 different paths gives you this opportunity. Here's another example, different cluster, that lensed a single object very extremely. It was just at the right spot. We call that the critical curve or the caustic. More about that in a minute. Redshift 6, which is 900 million years after the beginning. And typically, this light gets distorted along 2 different paths that are symmetric. So that cluster, star cluster, and that star cluster is an image of the same thing somewhere in that galaxy behind the cluster. And this blob and that blob is an image of the same elongated star cluster and so on. But there in the very middle of what we call the critical curve was a single star that has no counter image. We call it Arundel, the morning star in classic Celtic language. And it is, it's actually a double star. It contains of a hot and a young component. And it's seen at a redshift 6. Now, the star itself would have been observed with a signal to noise of 10 to the minus 4 if the cluster hadn't been there. The cluster provides a magnification of 10,000, and therefore the star becomes visible in a long Webb image. Barry, question? Yes, you can, and I'll get to that. We will see that stars can indeed cross the infinity line and momentarily become extremely bright for not very long, maybe only a few months. Here's a different cluster, G165, redshift 0.35, about 4 billion years in the past, selected as one of the brightest infrared sources in the sky with the Planck satellite. That was because there are these excessive star-forming galaxies that ordinarily look like that or like that, but they're right behind the cluster, which has 2 components, and they get highly stretched or spaghettified into these beautiful arcs. And in this arc, our own Seth Cohen found a supernova, which later on we showed was a redshift 1.78 with 3 images. And I'll show you, there it is, and there, and there. This was found, Seth, in March of 23. And immediately our team asked for more time from the director and got 3 more observations. And since we had a hunch that it could be a supernova type 1a at this redshift, we could therefore, with relativistic time delay, really refine the value of the Hubble constant. And with all these image families that are different objects, well, often images of the same object at different locations, different light paths behind the cluster, we could make a very accurate mass model of this pile here and that pile there and that pile. And all together they produce this stretched arc and that one. And there's the supernova image A, B, and C. And they didn't arrive at the same time, so they weren't equally bright because the light path from that location somewhere here to there, I think it appeared here first and then there and then there. And this is how that works. The supernova light curve, when the brightening happens, comes with this double hump, and then it decays because the elements like nickel and so on that are produced in that process have radioactive decay, and the brightness, and due to the expansion, just decays. And since you know the intrinsic brightness, this is an apparent flux scale in logarithmic units. We know the intrinsic brightness of these supernovae. They behave to a good approximation like a standard candle locally in our galaxy. We can actually derive a value of the Hubble constant because we got these 3 independent light paths. And with various methods, our best estimate was 75 kilometers per second per megaparsec. which is the expansion rate, how much faster the universe expands for every megaparsec increase in distance. And with a very large error bar, this is Adam Ries's value over here from the local distance ladder work. And here's the microwave background with its extremely small value. That's much smaller, 67 as opposed to 73. Today, these values are more than 5 sigma apart. And ours is on the high side, but with an error bar that's large enough based on a single object that we can't quite say that Adam Ries is right and the microwave background is off. This whole explanation for this, Dr. Kevin Croker about this, could have to do with the nature of dark energy and whether dark energy changes over cosmic time. So both could be right. This is measured at a redshift 1100. This is measured at a redshift, well, the magnification happens at redshift 0.35, but the source is a redshift 1.78. But there's our value. And the beauty of this is that these two obscenely bright, dusty star-forming galaxies produce more than 100 or 200 solar masses worth of new stars a year, which means that in principle, you should get more supernovae if you observe this longer. And so I started asking the question based on the work that my student Nick Fu and postdoc Patrick Kamineski have done recently. They observed another cluster here with a very large number of these dusty red, highly lensed objects. And how can we find more clusters where the supernova rate is so high that we can get more of these lensed supernovae? And the answer is we pick the brightest Planck clusters with regular merger-driven or chaotic star formation. You can see this here in the velocity maps. This is done with the ALMA telescope from the ground, sort of a Keplerian rotation curve for a regular galaxy. I think it's this blue one over here, and sort of a merger, which is this pile over here, and then sort of cigar-shaped or train wrecks, for this feature or that feature over there. And all of these processes happen. Some are regular, some are chaotic, but they all produce very much enhanced star formation, which is anywhere between a factor of 100 or 1,000 larger than our own galaxy. Our own galaxy doesn't produce more than one new star a year, so supernovae go off every few centuries. We're actually behind in that. In these galaxies, we can expect supernovae to happen every year. Here's the evidence. Hope you can read this. We picked the most massive clusters that have their largest Einstein angle for the gravitational lensing, and therefore also because the light paths are more or less constant. If the mass distribution is more or less spherical, the time delay in days, and this is almost a straight line, and we picked the ones with the largest Einstein angle and with the largest time delay within reason, bigger than 100 days, a couple of 100 days in the rest frame. Then we also make sure that on the scale of supernova rate production, type 1As or the core collapse supernovae, they produce anywhere between few a year to several a year. And if we're lucky and observe some of these clusters several times a year for a couple of years in a row, of course, we submitted proposals like this yesterday, then hopefully we'll get more of these type 1A supernovae at cosmological redshift that are multiply lensed, and then bring the error bars of this measurement way down. And this is completely independent from anything that's being done locally on the distance scale or the microwave background. It just assumes that these type 1A supernovae are standard candles. Yeah. Well, yeah, there's always, in an image like this, I'll take this as an example, there is regions inside where the magnification is, objects lose their light. So only objects at the right location behind the cluster get magnified and stretch into these arcs. But the total integral over the cluster lensing is 1. So there's also locations where lensing behind that cluster isn't effective. You just have to have an object at a lucky location. That's why you observe many, so you hope to get some good detections. Yeah. It's a great question. All right. So here's another lens supernova behind this galaxy cluster seen with Hubble in 2016, various images. And then Webb saw another, not the same supernova, more distant, redshift 1.9, about 3.5 billion years after the Big Bang, 2 years ago. So Webb And supernova lensing, lensed supernova, is the gift that keeps on giving. Here's another one, 2.9 billion years distance behind this cluster. And there are three sets of images of the same galaxy pair, distorted in different ways. And one of them clearly showed this image here, showed a supernova that went off a few years ago. Unfortunately, this was not triply lensed, so it couldn't be really used that well for Hubble constant. But supernovae go off all the time. Here's a very massive cluster that we also observed, Abell 2744, 10 to the 15 solar masses. It's only 4 billion light years away, but it gravitationally lenses about 5 young galaxies shown in these panels here, all distorted in different ways at a redshift of almost 8 when the universe was 670 million years old or so. So Webb is looking back to 650 million years after the beginning and providing you high resolution images. Remember, many of these are stretched to beyond their own intrinsic size that you would measure if the cluster wasn't there. So you get really a good chance of getting a high resolution image. This case in point here by one of our collaborators, also postdoc Patrick Kamenetsky, a rather distant cluster, redshift 0.9, called El Gordo, or the giant, the big one, which lensed a background galaxy almost completely into a pencil shape. The critical curve would be here. You can see the symmetric parts on both sides. And in the corner here, these three galaxies lensed a star-forming object into what we call a horseshoe, or Einstein's horseshoe. Here's an example of it. El Anzuelo in Spanish. It was our friend Quema Diego that analyzed it first. Fish hook is what it means in Spanish. And it does look like a fish hook. When you get the PDF file, look at this website here. There was a fellow in a public talk that I gave on this almost 3 years ago in Gold Canyon. He was 93 years old back then. And he was a Holocaust survivor. As a kid, he moved from Nazi Germany to Princeton. And he lived in the same street as Einstein. And he knew Albert Einstein. Go to his office and his house, and Einstein played the violin for him. And while Einstein never saw these images, didn't think he could see them, at least Warner Salinger got to see them all right. This is our best image so far, probably. It made it above the fold in the New York Times Science section, Christmas 2 years ago. Christmas time in the cosmos, a cluster redshift 0.4. What's so special about this is a region here where a couple of galaxies get highly magnified. And as Barry asked earlier, some of the individual stars in these galaxies made it across the critical curve. There are this, I'm not going to show any graphs. It's just easiest to imagine. It sort of looks like a hammock that you hang between the trees. And if you sit in the hammock and you let a marble go, it won't travel along a straight path, but it will do a curved path. And if you be at just the right location, looking through this gravitationally distorted field, there won't be a single path from the star to your telescope, but maybe 100 or 1,000 or 10,000 different paths, as you could see in this earlier arc-like structure that I showed here. This one, there will be many hundreds of paths from that object to your telescope. So the magnification in this case can be close to a factor of 10,000. And that's also the case here. Let me go back to that, where we saw individual stars up to redshift of 2 highly lensed, and we could distinguish one as a double star. This is the image that came with the NASA press release. It's 122 hours of Hubble and 22 hours of Webb. Those go at these relative exposure times about equally deep, because Webb is 6 times bigger in area. And if you just look at the Hubble image, it looks like this. Look at this galaxy barely visible. If you look at the infrared Webb image, you can see all the dusty objects in the background, or very high redshift objects in some case, shine through very well. Yeah, so here's an example of that critical curve business. I have a few minutes left, so I'll talk about that. This is an ordinary spiral, much like our own, but very highly stretched. And individual stars in this spiral galaxy that are close to this critical curve, which is where magnification can become infinity, but only for things that are infinitely narrow in angle. Stars are still 10 to the minus 10 arc seconds across, so the magnification goes as the square root of that. They will never magnify more than a factor of 100,000 or so. But you can see individual stars in these panels, the various epochs that were found by subtracting successive exposures. We had 4 epochs. And so all of these stars were close to the critical curve and were at least temporarily in that hammock-type landscape, highly magnified. 44 stars in a Nature Astronomy paper, a redshift 0.7, so almost half the Hubble time back in time. So we can be in the business here of counting individual stars. Why is this so important? Because you can now compare cold dark matter models with warm dark matter models with a scale of 15 or 100 parsec for the scale factor, the size. A parsec is 3 light years. And the important thing is that the location of where this crossing of the infinity line occurs is different from cold dark matter, where it is sort of symmetric around the critical curve, compared to warm or wave dark matter, where much of the occurrence is on one side of the critical curve. One of the magnification is on one side, especially if the scale length is small. And you see that in the data here, the distribution of these 44 caustic transiting stars compared to the center of the model critical curve is asymmetric. It's tilted to the right. And the psi dark matter, the wave dark matter model sort of follows that, while the cold dark matter model is clearly tilted in green to the left. So this is tentative evidence that psi dark matter needs to be taken seriously. What does this mean? Well, if it were particle that's ultralight, 10 to the minus 22 eV, then its de Broglie wavelength will be 10 parsec. And that's exactly the scale you're dealing with. So if we get enough statistics on these, we could begin to make the case that maybe that dark matter is an axionic lightweight particle. Here's another paper that's now in press as of a few days for Nature Astronomy by the Tom Broadhurst and Alvaro Pozo's group in Hong Kong and Spain. And they find that if you look at the images, that many of the galaxies that Webb sees are elongated. We've known this for a long time with Hubble. We call them chain galaxies or tadpole galaxies. There's a more recent paper called the banana galaxies. They're all the same thing. They're sort of highly elongated, more than they should be. If you make a cold dark matter model of the gas and how it forms into stars, as you will see more often than not, the cold dark matter gives you round, small objects, while the wave or psi dark matter gives you more elongated and bigger objects. Here's that in a graph. Imagine a 3-dimensional football or an ellipsoid, where A is the major axis, C is the minor axis, and B is the middle axis. The disks would be over here, the cigars would be over here, and the footballs would be over here in this diagram. And that's important because these are numerical simulations with the psi dark matter model, and here it is for the cold dark matter model. And the contours in the background are the data from the Hubble and Webb Sears and Kendall surveys. And so galaxies come primarily in smaller sizes according to the contoured data, with also smaller eccentricities. And that's well captured here. The eccentricities are sort of around 0.4, 0.5. The sizes are small, which is exactly what these two models give you, while cold dark matter gives you rounder galaxies up here that are also smaller. So hopefully one day we'll understand if this is indeed compelling evidence for cold dark matter not being quite the right model, but you need to look at these axion models. I'll stop with a couple of pretty pictures in the end and do a little more speculation on the black holes. This was a lensing cluster that lensed some globular clusters here in this arc, redshift 10. That's besides the point right now. If you look hard enough in many of these galaxies, and they're now redshift 1, you can see the central monster being present. It's a very crowded environment. Our galaxy would be one like this, but far away from this central massive cluster. Fortunately, we live in a cosmic, relatively quiet place. Why do I bring this up? Because in the deepest image of a cluster so far, you can see hundreds of these galaxies with a star-like pattern that carry a central black hole. And that is very common, especially for galaxies long ago, to have started forming with a massive black hole. We had one extreme example ourselves. I can't resist showing this all the way from the Lyman alpha to the H alpha filters. It sort of looks like the same banana shaped. And there's actually a radio source here with contours in green, where the central black hole is here, and a relativistic jet comes out and produces no fewer, triggers no fewer than about 1,800 solar masses a year worth of star formation in this object. And it contains a little less than 10 to the 11 solar masses. So this beast wasn't formed until 44 million years before you saw it. So right around redshift 4.2, and we observe it right here, redshift 4.11. This is courtesy of that supermassive black hole that's in the gravitational center, which is currently at the south side of this object. And this is fairly common, that black holes form early, and they may have in fact formed before the galaxies. This is the black hole mass measured from velocity dispersion, center of galaxies versus the stellar mass. And locally, you see that they form a nice regression with a lot of noise, but typically 0.5% or so of the galaxy mass makes it into the supermassive black hole. Redshift 4 to 8, that's not the case anymore. It's more like 10 or 40%. And so black holes form early before the galaxy gets triggered. Stated differently, who formed first, the chicken or the egg? Most certainly, the egg came before the chicken. The supermassive black hole came before the galaxy, at least in most cases. So for the sake of time, I'll skip this and I'll give you my conclusions. So I've said all this. I will not say it all over again, but the cosmic circle of life is one of the big themes of Webb. And then observing the first galaxies and the first stars and how galaxies assembled over the last 13.6 billion years, possibly triggered in many cases by supermassive black holes who came before the galaxies. So from dust we were made, and to cosmic dust we shall return as a solar system. And we're cosmic late bloomers, and we live in a relatively quiet place. We weren't formed early, and we're in the outskirts of a massive cluster. So thank you very much. I'll leave it at that and be happy to answer more questions. Yes, Barry, I need to eat some dark matter. No, it's a very good question. So they all are only visible because they're magnified by a factor of 1,000 or 5,000. And so that's what we call the top of the luminosity function. So the more massive stars that are intrinsically the brightest. And we could not have possibly seen them without the lensing magnification, which due to the crossing of the caustic is temporary. Yep. Yeah, great question. Over here. Yeah.
Observer, meaning our location.
The location of the solar system doesn't matter as much, but it does matter exactly where the source is compared to misplaced. My pointer. So in order to see an arc here and a counter arc there, the source has to be somewhere behind this, what we call the central cluster dominant galaxy, which is probably 10 to the 12.5 solar masses or so. If you move a little bit in the solar system, the pattern would still look the same. If you move over by 20 million light years in our solar neighborhood, outside our local group, then you would get a different pattern. Yeah. Yeah.
Time cluster, what's the Einstein?
The Einstein angle is, yeah, sorry, I should have. I'll go back to the Biden image, for lack of a better word. So the Einstein angle, if an object is right behind the central mass and it passes this and that counter arc, that angle from the center to here is the Einstein angle. That's the Planck Observatory. It's a far infrared satellite. Yeah, it's named after a famous physicist that you and I appreciate. They measured the Planck curve of the microwave background, amongst others. Yeah, that's why they call it the Planck satellite. I should have said that. Thank you. Other question?
So I'm reading somewhere that everything in the universe will eventually turn into iron, or like that.
there's a fusion and whatever. So I'm wondering the periodic table that you had. Guessing based on time.
Well,
I'm wondering what iron.
iron is at the minimum energy of, or maximum binding energy per nucleon, as you know, in the, I don't have a chart on that, but I'll stick with this. So typically nuclear fusion goes from hydrogen, helium, carbon, nitrogen, oxygen, ends up here, star gets hot enough. And only the processes that happen during the merging of neutron stars or explosion of massive stars can give you the heavier chemical elements. And I need to say I blank out for the moment as to the earlier question, how come some of the low mass stars can still produce these? If, you know, nuclear fusion in the end stage, the outer layer goes on just long enough, that can happen. But as you can see here, I mean, you try to find carbon, nitrogen, oxygen in this graph, there it is. But anything past iron is a dot smaller than a pixel in this image, so, yeah. Other questions? Yes, please. Yeah.
Also, are there examples where we know that a certain planet has water in it?
Yeah, there is water and carbon dioxide or carbon monoxide are commonly seen. You could find oxygen, we haven't seen it yet, or even ozone. If you see ozone, which we haven't, then that would be an interesting building block of life, or at least pointing in that direction. Water and methane and carbon monoxide are the most common ones. Yeah. Yes, question over there. Yeah. Yeah, it's in the yellow region here, it's due to shock. So it's the pure mechanical energy from that relativistic jet that compresses the gas. Yeah. And also turbulence, you know, the usual culprit that makes stars even without a relativistic jet. Yeah, good question. Yes, please. Cold dark matter, we have no clue what it is. We go back to that graph.
Why the word cold in there?
Because the velocity dispersion is very small. The temperature is very small. It doesn't interact with baryons. It just sits there. Psi dark matter or warm dark matter has a temperature, or more precisely a wavelength, if it's caused by axions that are inversely proportional to the size scale where they act. So 10 to the minus 22 eV is 10 parsecs. And that's a popular scale. I don't know whether it's right, but it seems to work. Yeah.
So obviously with a mass of 10 to the negative, that would not be really a false clump. And so, but, so what I have read in the past, a very low temperature at relatively high particle mass for dark matter, right? Explain conservative clump. And so, are you able to raise the temperature of dark matter? That's getting more dark matter while still preserving the function.
Yes. So the thing about psi dark matter or wave dark matter is that you can't have clumping on scales smaller than that de Broglie wavelength, which is 10 parsecs. So it actually initially prevent things to form at that scale. And sort of globular clusters form at that scale, but not smaller. So clumping, of course, in cold dark matter occurs hierarchically. It's a power law. You have more of the smaller things, and it goes all the way to infinitely small sizes. That's not true for warm dark matter because it carries a temperature or a wavelength that below which you can't form anything. Yeah, good point. Other questions? Paul? Yeah. Well, yeah, I said it's sort of tongue in cheek. What I really mean is that we're lucky we don't live here at the end of this relativistic jet, right? Yeah, or right next to all these beasts over here. I mean, this is good. Yeah. No, we live in an average part. Yeah. We're a bit of a cosmic afterthought, having only formed 4.5 million years ago, right? There's things out there that are 3 times older today. Okay, other questions? Oh, sorry, I couldn't see. Go ahead. It can, yeah, there's papers on that, yeah. 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 No, I think it's sort of a power spectrum of different lightweight particles. And I can't say that this 10⁻22 is the only one that works. There's, you know, heavier ones that would work. We don't know the final answer yet. It's a good question, though. And you know, bless his heart, George Smoot, who recently passed away, the Nobel laureate, really worked on this with Tom Broadhurst in the last few years. He thought this was the cutest thing. We could actually say something about these lightweight axions from the cosmological data. Any other questions? I know it's time. Well, it's overtime. What can I say? Webb launched late, so I went overtime. Thank you all. Yeah, yeah, who would have thought? After 25 years, the damn thing finally works. So my wife asked me on Christmas Day, 21, Roger, when will you retire? I said, well, either next week if the French dump it in the ocean, or in 5 years when we run out of gas. It turns out we have 27 years worth of propellant, so I'm condemned to 20 more years of hard labor. Yeah. No. Yeah, that's me.
I guess one question to ask. So the psi dark matter model is an example of this. It's a superfluid, right? Because of the dark matter forms of Bose-Einstein constant atom scales. I guess this is one question I've had for a while. Why do we not yet have enough experimental evidence to distinguish between something which is coherent on galactic scales versus something which is coherent on less than atomic scale?
It's because the physics could be so different. We understand the physics of atoms and molecules pretty well. We don't understand the physics on these very large scales really well, especially if it involves quantum particles. If it's all baryons, we understand that pretty well. That's just a matter of Newtonian calculations with a little atomic physics. Once you get quantum particles involved, it becomes a